instant about recording and putting things up on YouTube, make use of it. Okay. If you do not have internet access at home, bring me a flash drive. I set one of mine somewhere. Bring me a flash drive. I'll put the video on there, right? You don't have a flash drive and a computer. All you have is a, iPod Touch with a broken screen, or a whatever you have. Bring me said technology that you can watch a video on. I will put video on said technology so you can go watch. Okay, so if you don't have internet, that's okay. If you don't have a computer, that's okay. The only thing I cannot deal with, right? I cannot put a video on I can't put it in a traditional picture frame. All right? Don't bring me a $5 picture frame you bought from Walmart. I can't do anything with that. Okay? But if you give me anything that plays video, we can deal with this. Okay? So we can get it there. YouTube's the easiest way if you have internet. If not, that's okay. Now, where's the length of the pendulum? What is the one equation that you have that gives you the length of the pendulum? And then there's a couple of derivations from that. Okay, it's this guy, right? T equals 2 pi square root of L over G. And that becomes, whenever we get to omega, omega equals square root of G over F, right? But that's our one equation. The only thing is you have to know the period, and we know the period, right? The period is 2 pi. So whenever I come over here and I'm going to calculate this, number one, 2 pi equals 2 pi square root of L over 9.8. L must equal what? 9.8, right? 2 pi divided by 2 pi is 1. Square of 1 is 1. It has to come out to be 9.8 to make this work. Unit. Meters. Check out units, if you will, for me here. I'm going to have meters. The 2 pi and 2 pi, right? Unitless thing here, except this 2 pi is a period. What unit should that period have? Period. Seconds. Standard period, right? And this should come out in seconds. So this entire side of here has to come out in seconds. Now, the 2 pi part, this part right here means nothing. This is meters, and this is meters per second squared, right? Meters will go away, leaving me the square root of 1 over seconds squared. That's the same thing as the square root of seconds squared, right? Which is the same thing as seconds. Boom. Right? It works. Right. By the way, this is a way to double check what units you should come out in. Okay? Just plug, remember this is from topic 1, just plug the units into the equation and work the algebra. Just with units instead of numbers.
So the equation is not supposed to work for small angles, right?
Correct.
But if you imagine a string 9.8 meters long, and then if you pull it back to the amplitude, which is 3.2 meters per problem, that's like 30 degrees angle or something like that. It's certainly not tiny.
Whenever you start getting 45 degrees, 30 degrees is my upper limit. Just guesstimating here, right? I actually consider 30 degrees is my upper limit. I prefer it around 10 or 15 degrees or less to really be comfortable with this. But whenever you start going back farther and farther and farther, yeah, you got issues here. By the way, would you want the string to be really, really long or really, really short to make this, angle be small? Longer. Think about it, right? Imagine the extreme, a pendulum that has a string that starts at the top of the Empire State Building, right? And comes all the way down to the streets of New York. All right? So there's a thing hanging over the end, the pendulum comes all the way down. You could take that pendulum and you could walk, it's so tall, right? The string's so long. You could take that pendulum from, let's say it's in the center of the block, and walk to the other side of the block, right? All the way to the other side of the block. You've gone, let's say 40 feet, compared to how tall is the Empire State Building? The angle still would be small, right? But the longer the string, more than likely the smaller the angle is going to come out to be. 2. 2 asks us for what is the position at t equals 1.5 seconds. Is this a sine or cosine graph? This is a sine graph, so we're going to use x of t, or x, or whatever, the position according to that time, position equals amplitude x naught sine omega t plus phi. Do we need the plus phi part? No. What is phi? What is phi also? Phase shift. Yeah, perfect. Phase shift. And this starts at the exact same normal spot. There is no phase shift. By the way, on the quiz, many of y'all forgot phase shift in that base equation there. I didn't count off for that part of it. I hit you for other things. That's not one I forgot. I didn't count off on that because in the packet they don't have the plus phi, because for the most part you're not going to have plus phi in any of the problems. Okay, so I didn't knock you for that. But phase shift is going to be the foundation of one of the units or one of the sections in option A, and the foundation for 2 of the sections in option G. Okay, you got to understand phase shift, or at least know what it is right now. Okay, just in that broad conceptual, simplistic terms, you need to know what phase shift is. Okay, now this is a flow chart, right? I'm looking for x of t, the position. What was the amplitude that I gave you back on the graph? 3.2. 3.2 sine of omega. Let's come back and actually look at this. 3.2 the amplitude. Omega is 2 pi over t, right? And I gave you t off the graph. Whenever you see a displacement time graph, I am giving you period and I'm giving you amplitude. Those are the 2 alarm bells that need to go off in your head when you see displacement time graphs, right? So come back here, that's going to be 2 pi over t, which is 2 pi, times, I want to know it at 1.5 seconds, correct? Times 1.5. Please make sure your calculator is in radians, otherwise all bets are off, right? What does this come out to be? 3.19? Unit. Meters. Sig figs. 1. How many sig figs did I give you? Let's come back here. 3.2 and 2 pi. Pi, you can assume, has infinite number of significant figures. It's a constant. If I'm listing things in terms of pi, that does not affect your significant figures. So you get 2 sig figs because of 3.2. Right, so this becomes 3.2. Interesting. Interesting, huh? It's at approximately the amplitude. Approximately the amplitude here. All right? Questions? That would be 45. Questions here? You good? All right. Which, by the way, this should make sense to you that it's at the amplitude. 1 times 1.5 is 1.5, right? Halfway between. Kind of should make somewhat sense.
I think it kind of makes sense because, to go with the amplitude, in fact, would be pi seconds, and pi is roughly 3, and 1.5 is half of 3. So.
Yes, and we're not fully at the amplitude, 3.19, right? So because of the roughness of it, but roughly, that's exactly what it is there. All right, next. 3, I gave you a mass, 0.75 kilograms. What is the total energy at 1.5 seconds? What equation do we want to use for total energy? What equation do you want to use? I'm sorry?
Omega squared x naught.
Yeah. Now, the beauty here is, let's see, E total equals 1/2 m omega squared x naught squared, I believe, correct? The beauty behind this is we actually don't care what position it's at right there. We don't care what position it's at right there. We're looking for the total energy. It's the amplitude. Yeah, some of that's going to be in potential, some of that's going to be in kinetic, right? But total, it doesn't matter. This is just 1/2 0.75 2 pi over 2 pi 3.2 squared. What does your total energy come out to be? Say that again?
I got 4.59.
4.59? Plug that in, I got 1/2 times 75, 1 squared, that all goes away, so 1/2 times 75 times 3.2 squared. 3.2 squared is, a little bit more than 9. Cut that in half, so you're looking at somewhere around 4 or 5 times 0.75, so I'm thinking, 3, 4, somewhere in there. Yeah. You can. It's just we don't have enough information to do that. Right? Basic kinetic energy, 1/2 mv squared. Right? I've got it down. I don't have a v. I can calculate v then. And we're going to do that before, and I'm going to do it a different way. But you could calculate v using, let's see, this was a sine graph, so we want to use v equals x naught omega cosine omega t. Right? The velocity equation that goes with that position equation. Okay, and you look in your packet, it's the one right below the sine position equation. Okay, so you don't have to think about that, you just look at the packet and there it is. But height. Uh-oh, now I got issues. I don't know height really. Okay? There's a way you can figure it out. There's a way you can figure it out from the kinetic energy part, maybe, and from this, and how much energy then is going to be stored. It wouldn't be much fun. You have to deal with angles there, and they're all, yeah, it wouldn't be good.
The height isn't just like this or
No. Here, and this is dealing with the pendulum. I probably should have changed this. You're going to start seeing with the pendulums, and the reason I haven't been concerned about it is because it doesn't really matter, okay? That's the beauty of this. It doesn't really matter. Lots of times with pendulums, you won't actually see a displacement x, okay? You'll see a angle, theta, here. Theta. It doesn't matter, right? That's an angular displacement. In other words, as a pendulum swings, what angle gets swept out, okay? What angle is the string at? Okay, it just gives us a way to kind of equalize out all pendulums, right? Because a pendulum with a little bit longer string length is going to behave differently, and height changes in an exponential fashion here. I mean, it becomes weird. Okay, so angle kind of equalizes that out. So you'll see theta lots of times there. One way or another, don't worry about it. Plug in what you see. Okay, plug in what you see. So here, what did everyone come out with 4.59? No, what is it? 3.84 units. Joules, sig figs. How many? 2, so it becomes what? 3.8. 3.8 joules. Last but not least, 4. I'm asked for the velocity. Now, let me set you up with 2 ways to solve this. You can solve using V equals x naught omega sine omega t. Right? You can solve for it like that. Now, you got to remember, by the way, you don't really have to remember, you just got to look at the packet. You got to remember which equation goes with what. And that's a plug chug. I'm not going to solve it that way. I'm going to solve it like this. Kinetic energy equals 1/2 mv squared, right? And the kinetic energy equal to 1/2 m omega squared x naught squared minus x squared. That's how I'm going to solve that relationship. I've got 2 equations for kinetic energy, right? Kinetic energy is what's on the left. Kinetic energy is what's on the right. So they make each other to solve. my 1/2 m's go away, right? They cancel out. 1/2 m can cancel out. This leaves me with omega squared x naught squared minus x squared equals velocity squared, right? I'm going to solve this through, because by the way, in your homework there was a derivation. This is kind of the this is the derivation to get to this other equation. I want to show you this along with solving it. V equals then the square root of omega squared x naught squared minus x squared. Everyone see that? So this is going to get us around to square root of omega squared times the square root of x naught squared minus x squared equals V. That's plus or minus omega square root x naught squared minus x squared. There's that derivation that we had asked about doing that. You need to use correctness to derive that equation. Okay?
Like on these equations, like other than the inverse K, like they like interchange.
Yes. Yeah, all these equations that we have used is for simple harmonic motion. Anything that operates under simple harmonic motion. Mass of a spring, pendulum at small angles, a bridge going back and forth, which is kind of like a pendulum in the wind. The waves. We're going to get the waves. Waves operate by simple harmonic motion. You either, whenever I draw a sine cosine graph, probably your first thought wasn't simple harmonic motion. It was, hey, it's a wave, right? Well, just so happens that waves operate by simple harmonic motion. Okay? So ocean waves, sound waves, light waves, all of those waves. Okay. This works for any of them. The difference between them is going to be how you apply the equations. The difference between pendulum and spring is what omega is going to equal to, right? Omega square root of g over L, or square root of k over m, if I remember correctly. So how you use them change, but the equations work, whatever. All right, so this becomes a part of chug here. What is this velocity come out to be, please? Negative. Shouldn't matter. Say that again? 0.226. Point what? 0.25. Meters per second. Sure. Sure. Make sure your calculator's in radians. Critical here. Make sure your calculator's in radians. Right. So this becomes V equals amplitude 3.2. 3.2 times omega is 1, right? 1. Sine of 1 times 1.5 is 1.5. So that's a plug show. 3.2 times sine of 1.5 equals 1. Sine. Oh, cosine. Thank you, Hannah. You're completely correct. Good question. It's the, let me come back. This is a sine graph, right? Sine position graph, which means the velocity, I got to use its velocity pair. X. Right here. This is the position equation. Xt equals x naught sine omega t. Its velocity partner is this guy. Okay? Its velocity partner is that guy. Sine switches to cosine. Sine switches to cosine. If you look at your package, you can right below that sine graph, or that sine equation. All right, so this is 3.2 times cosine of 1.5, which should also give you the same velocity. Okay. Cosine 1.5.
Questions?